All right. Well, welcome to the last official class of 162. I can't believe how quickly the term went. It's one of these things where, actually, the last time I taught 162, we had an extra week worth of classes. So, unfortunately, there's material that we're not going to get to. But I thought I would talk about a couple of topics in brief, security and cloud computing being a couple of them, just to give you a little bit of interesting things at the end here. So, what is computer security when people talk about it? So it's basically computing in the presence of an adversary. So when the internet was first formed, of course, it was one big happy family, and nobody hacked into other people's computers except for fun. And, and the notion of never destroying anybody's data was sort of implicit in all of that. And the other thing that sort of comes along with security is you need to have reliability, robustness, fault tolerance, all of these things built in because of the size of the internet as a whole. And some of these things can be used to help you with security a little bit too, because you've got redundancy involved. But by and large, security is, loosely speaking, dealing with the actions of a knowledgeable attacker dedicated to causing harm. This is kind of the way things have shown up these days. And you want to be able to survive malice rather than just mischance. Now, last week we talked a bit about Byzantine agreement, which is sort of that extreme form where you sort of try to keep making decisions even when there are malicious elements in the system. Security is a little broader than that, and so I want to talk a little bit about it today. But of course, wherever there's an adversary, there's a computer security problem. So, protection versus security is something that's pretty important to talk about, and I don't know, sometimes when people think about security, they're really confusing mechanism or protection mechanism. So protection mechanisms are things that you put into the system like page tables and round-robin scheduler and data encryption and all of these things that can help with security, but just because you have these things doesn't mean your system is secure. Okay, so security is really using these mechanisms to prevent misuse of resources, and it's using such mechanisms with respect to a policy. So you have to know up front what is it you're trying to prevent, and then how do I use the mechanisms or protection mechanisms to do that? Does everybody see the difference? So protection mechanisms are just things you could use to put together a security policy. Security is really the whole package. And the other interesting thing that people often forget is they forget the simple things like, you've got the most secure system ever because it's been analyzed by zillions of people, but somebody walks out the front door with a flash drive that has all the important information on it, right? So, it doesn't matter what security you've put into place if there's an inside person that's willing to breach your security. So what are some requirements to get security? Clearly, we need to be able to identify people, ensure that users who they say they are. There's lots of ways to do that. If we had, an extra lecture or two, we might talk about some of these. Clearly, passwords you're all familiar with. Today, biometrics are kind of becoming very popular. I've got this little fingerprint scanner on my laptop, which is kind of a toy version of that. But this idea of somehow actually figuring out who a person really is an important part of security. Integrity is another important thing, which basically says that I put some data in there, and it's not possible for somebody else to change that data if they don't have permission to do that. Okay, and data integrity problems are kind of both subtle and pernicious because somebody may change data out from under you and you're not aware that they've changed that if your integrity mechanisms aren't good enough, and then you go ahead and act on the data as if it's the data you put there. Okay, and so data integrity issues are actually pretty important to decide ways of preventing this sort of substitution attack. Confidentiality, of course, is also very important. So our data gets stored everywhere these days in the cloud. What the heck does that actually mean? I like to, every time I hear the cloud, I've been around long enough that there wasn't a cloud once. And of course, the funny thing about the cloud is, what the heck is it? Is it a bunch of moisture in a machine room somewhere? Well, probably not. Is it a bunch of machine rooms somewhere? Yeah, I guess. But the interesting thing about this is how many people store confidential data in cloud storage? Okay. How many people have absolute faith that confidential data will not be breached? Okay. All right. Now, maybe the reason you have absolute faith is you're encrypting it yourself. Yeah, but be very careful, okay? Because we've seen a lot of confidentiality breaches of late, and they've been pretty bad ones. People's social security numbers, people's medical files, people's credit cards, all that sort of stuff. And then finally, what's also kind of an interesting thing is people like to say one thing and then claim they didn't. Okay, and so this idea of non-repudiation can be pretty important as well. You want to make sure that when somebody sends something, they can't later claim they didn't. Okay, because you can put all sorts of things in motion by saying something and then later, I didn't say that. Okay, how many people have had that common conversation? Okay, this happens in human interactions all the time. No, I didn't say that. They made that up. All right. You'd like to have your cryptographic mechanisms help prevent those kind of going back on your word, and this is basically called non-repudiation. So a lot of these things are kind of interesting properties we'd like to have of systems, and of course the one hammer that often gets applied in all of these cases is cryptography. Right? I mean, the cryptographic hammer is kind of something that, many of these things look like nails. When you have cryptography, you have to be a little careful about how you use cryptography in order to make these work. And I'm going to say a little bit about how cryptographic mechanism can help. Are there any questions about these sort of requirements? Everybody familiar with all of these things, pretty much? It kind of makes sense as part of sort of real life, right? So, in some sense, you could think of every communication across the internet, every storage of data on a disk drive is really a secure communication that you'd like to prevent, adversaries from dealing with. And basically, cryptography is a way to secure that. Cryptography's been around for thousands of years. There's actually a pretty fun book from Simon Singh called The Code Book, which you might want to look up if you're ever interested. That gives you a history of this. Obviously, it's mostly come to the forefront in the last century. And the central goal of cryptography has always been a confidentiality. So the idea is, how do I encode information so an adversary can't get at it, but a friend can? And the general premise behind this is there's something, which we'll call a key, the possession of which allows me to decode, but if I don't have the key, I can't decode. That's fundamental property. And, obviously the key has to be somehow kept secret, and it can't be guessable. And sometimes people sort of think of passwords and keys as the same thing. They can be, but the problem is passwords often have the connotation that you as a human can remember them somehow. And the notion of remembering versus not guessable are not necessarily compatible with each other, because the thing you can remember may actually be easily guessable if somebody knows something about you. So that's kind of interesting, right? Now, let's look at a very simple example here, which is called symmetric key. How many people have dealt with cryptography before? Have this been done in classes at all? Okay, some of you. So a symmetric key is a very simple scenario in which the same key, which is a set of bits, is on either side of the communication, and what happens is you take plain text, which is the word for unencrypted data, and you somehow munge it around with a secret key, and what comes out is ciphertext that you send over to the destination, and then they do the reverse process to get the message back. And this key is the same on both sides, is one thing. And the other is that we have to make sure, obviously, that this key has been distributed beforehand, because you can't just transfer the key through the internet, otherwise people will know the key. So immediately when we start talking about cryptography, we worry a little bit about key distribution right off the bat. Right? And the thing about this sort of primitive version of this that I've shown you is that this is vulnerable to tampering and replay attacks and so on, because if you don't do this correctly, it's possible to take a little encrypted message, and yes, it goes to the other side, but then an attacker sort of stores it in memory and then sends it later, and you don't know the difference between the attacker sending it to you and getting it as an original message. That's called a replay attack. Okay? So those things aside, what's the essential property we're counting on here about the ciphertext? What are we assuming to make this scheme even worth considering? Yeah. That's right. So the essential property is somehow it's not possible to go from the ciphertext to the plain text without the key. And what's interesting about that is, for instance, it's possible that you're not clever when you're doing this encryption, and if somebody were to store up enough ciphertext messages, they could eventually figure out what you're sending just by sort of knowing what you're going after. And so you got to be very careful, because just because one message isn't reversible doesn't mean that multiple of them aren't either. And so these schemes are not just, how hard is it to decrypt one message, but what does a set of messages help you with? And I'll say something about that in a second. So, for instance, one thing you could do is you could just take every message, and you've got this long key that you've prearranged, and all you do is you just XOR your data with the key. Okay? And now you send your Berkeley manifesto, and you send it to somebody else, and the problem is that somebody who's watching this, just because you've XOR'd, you haven't actually changed the frequency of any of the data, and they could do a frequency analysis on the data you're sending, and they could figure out that an A is a certain frequency in the English language, and a B is a certain frequency, and so on, and they could figure out just by doing a frequency analysis. So that says that you got to make sure that when you send multiple A's in that message, that they all look different each time somehow. You can't just have every encrypted A look the same. Okay? Now, there is this idea of using what's called a one-time pad, and this has been used in various combatant scenarios where there's actually a prearranged code book, and you do XOR it, but you basically, every time you use up a digit in your key, you throw the page away, and that is basically unbreakable. Okay, because unless they know how you generated that code book, they can't really do any frequency analysis or anything on it. The problem is you're distributing a book or a lot of data to somebody before the communication, and that's kind of inconvenient. Okay, so more sophisticated versions of symmetric keys are what are called block ciphers. And the idea here is that you take your plain text, you break it into blocks, and for each block, you operate the key on it. That generates ciphertext, which goes to the definition and to the destination, and you do the opposite. But what's interesting about this process is you do feedback in here, so that when you encode the same block multiple times, it looks different each time. And you make sure that whatever feedback mechanism you use on one side is known on the other, and that's kind of a more sophisticated block cipher scheme. Okay. The other thing you can do, by the way, is you can also have just a counter that increments that you add into part of this, and that becomes a way to make sure that sort of every version of the same data looks different. Now, there's a lot of symmetric keys out there. You've probably all heard of DES, which was the data encryption standard. This was originally developed in the 70s and standardized by various government agencies. For a while, there was conspiracy theories that the NSA had put backdoors into DES so that it was easily breakable, and then they got everybody hooked on it. The biggest problem with it now is it's got such a small key space that you can just brute force run through all possible keys and break it. So anybody who still uses DES does something called triple DES, where you have 3 keys and you do DES, DES, DES. More recent is this AES standard, which I'm sure how many people have heard of AES? Anybody Okay? So AES was a replacement for DES, came out in 2002. And the nice thing about this is built into the algorithm is the possibility of a lot of key sizes. And so if you're really paranoid, you use 256 bits. Lots of people use 128 because it's still pretty strong. But how strong is it? Well, there aren't any proofs really that any of these things are unbreakable because they're defined not really mathematically, but a whole series of you exchange these bits and then you shuffle this and you put the key in there, and it's very hard to get a proof of strength of these things. But most people believe that the AES standard is quite strong. Okay. So how do we use this for something interesting, like let's authenticate to prove who we are? So the main idea is that entity proves who they are by using this secret key K shared by A and B. And so what we could do here is that A is going to ask B to prove to A that B is B. And so what we can do is A is going to, sorry, this got out of order here, but A is going to send a message to B where they pick a random number X called a nonce. They're going to encrypt it with K and send it to B, and then if B is who they say they are, they should be able to undo that and send X back. Okay? And notice that the essential assumption here is that the only two people in the world who know K are A and B. All right? And this is a fairly simple scheme. The downside of many of these schemes that are simple is that somebody in the middle who can intercept these messages lets E go through, and then when X is coming back, then they start communicating with A pretending that they're B. Okay, and so that could be a problem. All right. Now, something a little better than that scheme is using cryptographic hashes, which are basically a building block for integrity. And the idea behind hashing is very simple. You take a big block of data, you run the hash over it, it gives you a small bit string. And what we can do is we can associate the hash with whatever our bytes are, and the receiver uses it to verify that things match. So the approach here we're going to talk about for just a moment is, for instance, suppose that we have M, and we want to prove to somebody that yes, this M is what we're sending, but we're going to prove that it's us. And so we start out with a hash function, h of x, and h of x is going to be known by everybody. It's publicly known. But we're going to build this, what's called a digest, and this is the HMAC digest, which takes the key and the message. And we do this with it. We take a hash of the key concatenated with the message, and then we hash the key concatenated with that result, and we send this thing off to the other side. And the other side can do the same computation given n, and they can say, oh, gee, the only person that could have sent that to me must be A, because they're the only ones that have the key. Okay? Everybody with the idea? Here's a picture of it, by the way. Come on. So here we have A and B. A is going to send M, could be either encrypted or not, doesn't matter. And then they're going to build this signature-like digest, which uses K and M. And at the other side, what happens is they take M, they recompute the digest, and they say, gee, does this match the one I got? If the answer is no, either the message is corrupted or it's not the real person over there. And if the answer is yes, we win. And we really only got that message M from the other side. Okay? Questions? Can everybody see how we can start to use mechanisms like this to build up interesting security policies? Because we can make sure that a message is definitely from the person who said they were, because they're the only ones that can have K. Stare at that for a sec. Now, it's surprising that nobody's asked the obvious question about HMAC. What's the obvious question? Why is it so complicated? Does everybody see what we're doing there? We're taking a hash of the key concatenated with M, and then we're taking the result of that and concatenating the key and hashing it again. Why do we do that? Does anybody know? Why not just send hash of K concatenated with M? want to stab a guess at it? Yeah.
What if the hash function is vulnerable to first bits being the same every time or something?
You're close. The real issue here is that hash of k concatenated with m, if you know that value, you can often figure out what the hash of k concatenated with a longer m that has this prefix of the original m, and so there's a whole series of messages that you can authenticate, which are just longer than your original one. And so there's definitely vulnerability to sort of concatenation attacks here. So, yes. Okay. And so there's lots of hash functions. Everybody's probably heard of MD5, right? If you've ever downloaded software and wondered whether you got the right thing, you probably had MD5. This has actually been mostly broken so that it's possible for if you have an MD5 hash of one message, to find a second one that has the same hash function. Much more secure are things like SHA-1, which is sort of broken, but not as badly as MD5, but even better is SHA-2. And this is, as far as we know, not broken, and it's a whole family of hash functions that produce 224 bits, 256 bits, 384 bits, and 512 bits. So what this really means is you take your big message, however many bits it is, you plug it in to the hash function, and you get this digest, which is that number of bits. And the important property of these secure hash functions, I should have put this down, is one, if you put basically if you hash a message and you get a hash out of it, it's not possible to figure out what the message was. You can't reverse engineer that. And the second thing, and more very important here, is you can't find a second message that has the same hash. Okay, those are basically important things that allow us to have this property here where when we get this digest, we know for sure that it had to come through this message associated with that key. And so those are essentially secure properties. Okay? All right. Any questions? Now, we can't talk about these mechanisms without talking about asymmetric encryption or public key. So the idea here is there's two keys, one to encrypt and one to decrypt. We'll call them key E and key D. It's basically a key pair. And the crucial property is basically knowing E does not give away D. So what's interesting about public key encryption, by the way, this is probably the thing that most advanced cryptography ever was basically coming up with these public key systems. And we can, because we know E doesn't give away D, we can give E to anybody. We can make it public. Okay? And so basically, if Alice wants to send to Bob, she gets Bob's public key, encrypts something with it, and the interesting thing about that is Alice can't decrypt again, but then neither can anybody else except Bob. So anybody can send message to Bob by encrypting with his public key, and only he can decrypt with his private key. So this is cool. It's very asymmetric. Unlike the symmetric key, where if I encrypt it with the key, pretty much I can certainly decrypt it, and anybody else who has the key can decrypt it. Okay, so that's the symmetric part. So asymmetric encryption lets you build all sorts of interesting protocols, and I'll show you one in a moment, but this is the basic idea. You encrypt with the public key, that gives you ciphertext, and you decrypt with a private key. Or, these things are symmetrical, so we could go the other way by encrypting with the private key and decrypting with the public key. Okay? So, questions? So does everybody start to see how you could build interesting protocols out of this? So for instance, if I want to prove to somebody who I am, I take some message and I encrypt it with my private key and send it out, and only I could have had my private key, so everybody can verify that I'm who I say I am, because they can check it with my public key. And furthermore, if anybody wants to send message to me, they can encrypt with my public key, and only I can decrypt it. So we can start building all sorts of interesting protocols out of this. And this public key cryptography idea was invented in the 70s, and it pretty much revolutionized cryptography. And how does this work? Typically number theory is involved. So, for instance, the most fully developed approach is the RSA approach, standing for three people, Rivest, Shamir, and Edelman, who constructed it. And it's used very widely. So every time you go to a website that uses, HTTPS, you're probably using RSA. Okay, and there's also another public key system which is becoming more and more popular called the elliptic curve cryptography. The nice thing about this is the keys and the signatures are shorter for the same level of strength. Now, So what are some properties of RSA? So you have to generate really large random prime numbers to make this work. How many people have an RSA public key? Anybody? Many of you? What do you use it for? Sending mail? Signing things? What was that? Git? Yes. Good. Thank you. You should have all raised your hands, right? Yes. So basically the process of generating an RSA public key basically involves generating two really large random prime numbers and then multiplying them together and generating some other things with them. So why is this not going? Hello? There we go. There's exponentiation that's involved here, which is mathematically intense, but people have a good handle on it. But overall, the key thing about, no pun intended, public key crypto systems is they are a lot slower than symmetric key crypto. And so what typically happens is you use public key cryptography to distribute keys, and then you use symmetric key cryptography to encrypt things. And I'm actually going to show you how the SSL protocol does that. Okay, that's exactly the way this works. And so basically, you use the public keys to help you with identity and key distribution. And how difficult is it to recover the private key D from the public key? Well, the answer is it's supposed to be very hard, supposedly. There are no actual proofs, but it seems to be sub-exponential. It basically goes with how hard it is to factor things. There is this rather amusing thing I say at the bottom of the screen here, though, which is that in theory, quantum computers, if they existed, could factor large prime numbers in polynomial time. And so you can kind of see a little bit about why, for instance, certain three-letter agencies who will remain nameless like to fund quantum computing research. Okay? Because in theory, if you had a large-scale quantum computer, you could break everybody's RSA keys. Okay. So here's how we could use public key authentication. So each side only needs to know the other side's public key. There's no secret keys that have to be shared. And so A might encrypt a nonce. Sorry about this. This is screwed up again here. But A might encrypt a random number that it generates just for this session called X. And maybe says what its identity is, and it encrypts it with B's public key. So only B can do the reverse, basically decrypt this, and now it knows X and it knows A, and it can send back X and a new random number Y that it generates and something that says it's B, and it encrypts it with A's public key, and now only A can undo that other side, and it can send back to B saying, hey, look, yeah, I did decrypt that, so I'm really A. So if you look at this exchange that's going on here, only public keys are involved, and when you're done, both sides have two random numbers, X and Y, that you can now use for symmetric key encryption. Okay, so what's cool about this is not only have we verified that A and B are talking to each other, but we've established a new random key that we can use for the faster AES encryption, for instance. Yeah, question? Why is it faster? So the reason it's faster is basically because both RSA and elliptic curve cryptography involve lots of complex operations that are basically Galois field operations where things are not quite multiplying and not quite dividing and so on. It's just they're computationally intensive. Whereas symmetric key encryption typically involves lots of bit shuffling, and you can do it fairly rapidly. In fact, you can build really fast symmetric key encryption, decryption hardware even. So, yeah, so in fact, the number that used to be thrown around, and is still pretty true with RSA public key encryption, is that it's about 3 orders of magnitude slower. Okay, so this is pretty much the way people both authenticate who they are and then generate a key for communication that's going to happen during that session. Good question, though. Any other questions? Yeah.
When we say it's 1,000 times slower, how significant is that usually compared to network latency and other performance?
It can be very significant when you start talking about high bandwidth networks. You know, you're talking about, well, I've got a gigabit or 10 gigabits or 100 gigabits. It's just the throughput that you can get if you were encrypting every bit with a public key crypto system would just be, you couldn't do it, basically. And there's almost no need to do it. I mean, the nice thing about this is AES is pretty secure. It's just the key distribution part that's the problem, and this is a way to distribute a random key that you've just generated for that one session. So this is like better use of your computational bandwidth, almost. Good question. So we can also use crypto schemes like this for non-repudiation. So Alice has their public key published, and she says, gee, I want to prove who I am. And so she sends a message X to the world that's encrypted with her private key. So she sends the encryption of X with her private key KD. And now anybody who knows Alice's public key can decrypt it and say, oh, yep, that message must be from Alice because only Alice has her private key. You guys are starting to see how this works? Only so-and-so has a private key. And if you look at a lot of these schemes, and it's looking, by the way, given the poll that I may be talking about Internet of Things, among other things, on Monday, a lot of these schemes that are out there assume that every device or most devices and most people and most cats and dogs, whatever, that are attached to the Internet all have private keys that are kept private somehow. And of course, now we start wondering about breaching hardware or whatever, so those keys get broken, right? But this is a form of non-repudiation. Given the assumption that nobody has Alice's private key, only she could have produced this encryption. And of course, this, by the way, I could just take the message and hash it and then encrypt that. And that's a typical signature where now the message could be in the clear. It could be my will and testament that I've hashed, and then I sign it with my private key, and that's how everybody knows that it's from me and not from somebody else. Okay, same idea. And the interesting thing is we're talking about communication here, setting up channels, whatever, but anything we're talking about here can also be like my communication channel is to a disk or a cloud storage service. And therefore, I store it in this public service, and it's got a signature on it. I can't repudiate it later because it's got my signature on it. And so we can talk about signing data that's even in permanent repositories that are kept for the lifetime of the planet or whatever, right? Okay, questions? Yeah.
I don't really get how this is like non-repudiation. If you wanted to repudiate it, you could give your private key to somebody else.
Okay, so the non-repudiation part is under the assumption that that you've not done that. That's right. Well, no, but if you're malicious and somebody starts signing things, going through and saying, I need to get a new public key and I need to basically repudiate everything that was signed with that public key is presumably not is something that people would know, and so they might question the fact that you've done this, right? So in order to do what you've said, you have to publicly state that my signature has been compromised, and that already raises questions. Yeah. So, here's what I just said here. For instance, Alice says, I will pay Bob. She encrypts it with her private key. It's decrypted to verify, and everybody knows that Bob's going to get paid, and Alice said they'd pay Alice. And again, if she gives her private key out or gets compromised, again, you've gone through the public embarrassment of having compromised your public key, or your private key, and so you may not want to do that. Okay. So what's a digital but the problem here, by the way, in all of this, assuming that Alice doesn't give out her private key, is how do I know what Alice's public key is? I mean, we're trusting that we can find Alice's public key, and this is where the idea of certificates come into play, which is interesting. And so here, we need to have a trusted authority. This is one version. How many people have heard of VeriSign before? Okay. What does VeriSign do? Well, their whole reason in life is to produce certificates. And what their certificates look like is they have a well-known public key, KV public, which I'll show you in a second, which has a private key that goes along with it. And what they do is they sign things that say, Alice and this public key go together, and we're going to sign it with our private key, and now this certificate is given out to the world. And what it is it is a statement by VeriSign on the strength of their private key that this is Alice's public key. Okay, and in theory, what's supposed to happen is Alice is supposed to go into some big VeriSign office and prove who they are with a birth certificate and all this sort of stuff, and then VeriSign will stamp their public key. In reality, that doesn't happen under most certificates that you can get. Usually you can pay money and get a certificate. So there's a little bit of a flaw in this theory. There are really high-level certificates that these authorities, that they charge you more for, that sort of require you to go and actually prove who you are. And so that maybe is more in the spirit. But what's interesting about this is now the question is, how do you get VeriSign's public key? Does anybody know? Yeah, so the only reason you have VeriSign's public key is because it's compiled into your browser. Okay? And by the way, we'll talk about that in a second. So Alex distributes her digital certificate C along with their communication, and now that means that anybody can extract her public key out of that and know that it's the correct public key on the strength of VeriSign. So you have to believe that VeriSign's public key is good. Okay? And so far, we're talking about securely distributing a key, which gives us symmetric ciphers with AES, which is fast, strong communication. We have public key cryptography, which is slow, but can be used to set up session keys and prove who you are. And digital signatures can bind public key to actual entities, and we can use certificates to do that. The interesting question, though, is if I have to have some entity that has got a signature of my key, and that entity, like VeriSign, has their public key in my browser, what happens, A, when a new entity comes online that's a signing entity? What do we have to do? We have to get a new browser, right, or a new update to your browser. More interesting, what happens if a signing authority that was in your browser has been proven to be compromised or malicious? You have to somehow make sure that that is known so those certificates aren't used, and you want to distribute new browsers to prevent it. And there have been a number of interesting issues along these lines. If you go to your browser, you can actually see what public keys are preloaded there. And what's interesting is there are of order 90 or so of these signing authorities, some of which are said to be foreign governments and not really very trustable. I won't say which ones, but an interesting problem. Okay, so the strength of all of this rests on something in your browser. So let's put this all together really quickly. If we want to do an HTTPS connection with, say, Amazon, because you absolutely have to buy a book tonight, you're going to go https://www.amazon.com. What actually happens? Well, this HTTPS thing actually means use HTTP over an SSL TLS layer. SSL is secure socket layer. TLS is the latest version. And in theory, this is supposed to set up a secure channel between you and Amazon. Okay? And it's fairly transparent to applications. There's that fun word again. It's supposed to be something that you don't have to know once the protocol is set up that it's there. Okay? So you could often write your web browser or web server software the same way if you're going over HTTPS as if you're not, and that's mostly true. There's some gotchas in that, but that's a whole different topic. And so let's look at this communication here. So your browser is going to connect with Amazon first, and it says something like, "Hi, I support TLS plus RSA plus AES 128 plus SHA-2," or SSL plus RSA plus 3DES plus MD5. What's going on here is a negotiation of protocols. And this, I was joking at how fast I said this, but notice those combinations are all things that you can mostly recognize in there, right? I'm using TLS, I'm using the RSA public key crypto system, I'm using AES 128 bits, and SHA-2 as my hash function. And so what first comes back is, okay, let's do this. We'll use this guy. Okay, and so that communication starts off by saying, what cryptography can you bring to the table? And it says, okay, that's fine. And the other thing that Amazon sends back is, here's my certificate signed by whoever signed my certificate, so you can know for a fact that this is my public key and who you're communicating with. So Amazon sends that certificate to me, and that's about a kilobyte or so of data back, so that now I can send encrypted stuff to Amazon by using that public key. And I can verify that it's truly Amazon. So that's an important step here, is to get this certificate. How many people have browsed to a site and you got an out-of-date certificate? Do you want to proceed or abort your transaction? How many people have seen that box? How many people have pressed, go ahead. Okay, you have just violated the main security here because you've said anybody send you back a certificate that's trying to prove the public key is owned by Amazon, and you've just said, well, I realize it doesn't check out, but go for it anyway. And you've just agreed to a potential man-in-the-middle attack. Okay? Now, usually it isn't one, but... so what's inside the certificate? Sort of name associated, namely Amazon, Amazon's public key, a bunch of other stuff like physical address and certificate type and expiration time, and who the signing person is, who signed it. That's the certificate authority. And all of this stuff is put together into a package, which you can then verify by checking the certificate that was sent there against the signatory's public key that's in your browser. This all sounds fine. Okay, except, how does the browser authenticate? So it's hardwired into the browser. And if it can't find the certificate or can't verify it, it'll warn that something's wrong. And you go ahead and say, okay, go anyway. So you've just violated the security. And then we get this exchange of nonces to get a random key set up for communication. And there you go. Now what's interesting about this is all assuming that the signature matches and you now have high confidence. But what's interesting is there have been some noteworthy exceptions to this. So like in 2011, there was a Dutch certificate authority called DigiNotar that their key was compromised, and there was a bunch of certificates for things like Google, Yahoo, Mozilla, all signed with that key that were fake keys and therefore supported somebody in the middle. In fact, there was even a Google general certificate that all the Google domains would verify with. And that wasn't discovered right away. And so as a result, because of this breach, you had these bogus certificates out there. And people could fool your browser into not even asking you, saying that there's a problem with your key, because the browser thought the key was fine. All right? And the funny thing about this, or not so funny, is the Dutch government at some point was not even admitting that this happened, and they didn't want people to find out about it, and so on. And if you look up this breach, you'll see that this company was bankrupt at the time, and who knows what actually happened. But there's some notion that at least 500 certificates, bogus ones, were signed before this was discovered. So, next time you, with high confidence, use your browser and type in HTTPS, you might think twice, but what else are you going to do? I mean, you're going to stop shopping at Amazon. I don't know. Yeah, question? When you do HTTP, there's no security whatsoever. Everything's in the clear. Everything can be observed by other people. Now, you may type a password in, but that password goes in the clear, and then, yes, Amazon thinks they're talking to somebody that's got that password. But if you're ever dealing with passwords or credentials or credit cards or anything that needs to be private, do not do HTTP. You'll always want HTTPS at minimum. Yeah, question?
Why do sites even allow you to put in your password over
they're badly written. That's a bug. I mean, by the way, it's very easy to write bad web server software. I'll be happy to show you how to do that. No, it's the problem is that people who are writing web servers or websites are basically thinking about the site, and they're not always thinking about security, and so, they might bolt on SSL at the end, and maybe there's a back door into their site that accepts regular HTTP requests, and then it goes to the same place that the HTTPS one does. Again, I said transparent earlier, and so the software that's running this is asking for the password without knowing whether you came in the HTTP or the HTTPS route. So that's the thing that's pernicious or kind of bad about that is that can be just a misconfiguration sometimes can allow that to happen. So, yeah. Okay. So here's the validation. I don't need to go through this in great detail, but the idea is the certificate that comes in is a signed thing that you independently check and you validate with the hardwired public key, so that lets you decrypt the HMAC. And then you check it yourself by doing the hashes and over the certificate, and either it works or it doesn't. So, okay. So then just to finish this up, Amazon says, here's my certificate. The browser then picks a random key, which is going to be a session key, encrypts it, sends it to Amazon. Amazon says, okay. And all subsequent things, like even your encrypted password, which we were just talking about, now is encrypted with this session key K. And so all of this communication is encrypted and safe. Okay, and so notice that we've used the public key encryption both to prove that we're talking with Amazon and to generate a symmetric key that then we use for all future communication. Right? Good. So, midterm 2 is in progress. It'll be done by Sunday, we promise. Solutions are up. Project grades. So project 1, sorry about this. This is kind of hard to believe that this was this way, but definitely tomorrow you will have project 1 grades for absolutely sure. Okay, we won't go into what's happening. You may even see partial grades pushed out. Project 2 will definitely be done by the middle of next week. Final exam. Oh, and we'll post info on regrade requests on midterm 2. Final exam, as you're all well aware, is on Friday the 15th, so that's 2 weeks from this Friday. It's in Wheeler Auditorium. We all get to be in one big happy place. And basically, in principle, it's all material from the class. You get 2 sheets of notes, both sides, and you should bring yourself a dumb calculator, presumably one that actually does add, subtract, multiply, divide, not quite dumber than that. And then as far as reviews, I think we're going to try something a little different. So apparently the way the reviews have gone is there's one review session and people come with a bunch of topics and only 2 of them get talked about. And so what we're going to try instead is have maybe 3 different review sessions, each with different topics on them. What do people think about that? We'll post this info on Piazza. It's kind of a way, and we'll have different TAs manning these, but it'll be a way to hopefully not cover things rather than sort of get stuck on just 2 topics. All right? Good. And then Monday is the freebie lecture. There's no final implications for this in the sense that none of the materials I talk about will be on the final. If there's a poll on Piazza, how many people have seen the poll on Piazza? Okay, if you haven't, you should take a look. If you haven't voted, you should. Right now, the upfront runners seem to be Internet of Things and quantum computing are the top 2. There's a close second for mobile OS, a close third, whatever. But you should go vote onto what you want. I mean, as it is right now, I may talk about Internet of Things for half and quantum computing for the other half, and maybe mobile OS will get thrown into Internet of Things. I don't know. But, all right? I've had a lot of people, well, what does quantum computing have to do with operating systems? Nothing. All right. Do people want a brief break, or should I? We're only going for another 15 minutes before HKN. Should I talk for a little bit more and then we'll take a break? Or yes? Huh? 2 many breaks.
I said 2 minute break.
Oh, you want a few minute break? People want a few minute break? Okay, we'll go for a 2 minute break. Stand up, greet your neighbor. Okay. That was a minute and a half. So I wanted to say a little bit, sorry about that, come on down. So cloud computing is an interesting thing that has really happened in the last decade. If you look back in the history of things, back in the 80s and 90s were really an amazing time for computing because we were getting essentially a doubling in the performance of processing every 18 months. And so the interesting thing about this was if your program was too slow to work, you didn't have to do any work to fix it. What you did is you waited a year and a half and then the program was fine because your computer was twice as fast. Okay? So that was the lazy man's computing time. Around 2002, there were all sorts of problems that started happening. There was a thermal wall that things got too hot. There was capacitance issues, lots of things. So speed basically tapered off, and transistors kind of kept shrinking. But what happened, so you could put lots of things on them, but you couldn't make it as fast. And so this 52% growth in performance just fell off. So things were not getting faster by much, but there were still lots more of them. And so that led to basically multi-core. And we said a little bit about this at the beginning of the term, but multi-core was kind of funny to some of us that were working in parallel computing before that because, all of a sudden it's like, oh, there's this new thing, there's parallel computing. It's like, well, parallel computing's been around a long time, but suddenly everybody had to deal with parallel computing. So that was really what happened. And that was all fine and dandy. But then around 2010 or so, suddenly we had something new coming on the horizon, which is so much data from everywhere that we had to start calling it big data. Okay, now there were big things before, but the data got really big. Okay, and so you guys are now in the decade of big data, to the point that we're even talking about, naming new institutes of big data here at Berkeley or whatever. I mean, it's the thing. There's certainly the AMP lab over in Soda Hall. And so there's many sources that are driving big data, but most, it's online issues, or it's all about the network, right? So in some sense, and if you think that you're off the grid, you're not, because every click, ad impression, billing event, fast forward, pause, friend request, transaction, network message, fault, all of this stuff is all recorded for all time. Okay? Don't do it online if you don't want to see it again. User-generated mobile devices are busy producing a lot of this data. There's this so-called Internet of Things, which is coming up, which is I'm going to put a network connection in my toaster and in my refrigerator and on my dog, and all of a sudden, there's all this data that's coming through. This is kind of an interesting thing that remains to be seen how useful it is. I think it's going to be quite useful. But This is the age of machine to machine. That's what M2M stands for. And of course, scientific computing on top of this data has really pushed it. And I wanted to show you this. What's interesting is things like the human genome projects and so on are really driving a lot of research, because what's interesting now is you can target treatments to specific illnesses or specific strains of an illness by doing a genetic profile on somebody who's sick and doing matching of that against the DNA database. And there's so much work on this that people are figuring out how to use better and better algorithms, and so effectively the performance is going faster than Moore's law, which is this thing that's driving the increase in number of components. But there's lots of sources and money behind big data. And so this data deluge, what are we going to do? So billions of users, World Wide Web, Facebook, Twitter, cell phones, so on and so forth. 80% of the data produced on Facebook was produced last year. Okay, so what's interesting about this is the data is growing kind of exponentially. And fortunately, of course, storage is getting cheaper. We talked about this earlier, the new Seagate drives that are 10 terabytes in a little 3.5-inch package. So it's not like we can't store the data. The question is, what do we do with it? How do we do something useful with it? Okay? And the amount of data, unfortunately, is growing faster than our components are growing. And so there's, examples here. Here's Moore's law growth, which is that growth in the number of elements on chips. And notice that the data coming off of even particle accelerators is growing at a faster exponential curve. And DNA sequencers are sequencing things faster. Okay, so the data is just growing at a ridiculous rate, and then of course we have social networks which are growing at ridiculous rates as well. So the data is big, there's a lot of big data, okay? That's probably easy to say. And so what do we do with the fact that computers are not getting faster and we're drowning in data? Okay, how do we resolve the dilemma? Go off grid. Oh wait, that was not an option. How do we resolve this dilemma? Okay, we got to do something, right? And so what big companies have done is they've gone massively distributed and massively parallel. And you see machine rooms like this. Okay? This is the kind of nightmare you used to have after watching The Matrix or whatever, right? You've got sort of seas and seas of computing components going off in, or maybe, maybe the Terminator, although you guys are a little too young for that, maybe. But these exist, right? Google's got them, Yahoo's got them. Even Google's talking about making floating versions because they don't have enough space for them as it is. So you float it out on this huge platform because the ocean's big, and lots of solar energy and so on, or wave power and so on. And so the answer to computing not getting faster at the same rate is you just put a lot of computers together and you got to do something with them. And so now we have massive parallelism and massive distribution of tasks. So enter the world of distributed systems. So when I started in computing, a distributed system had 20 computers that somehow collaborated together. Okay, now a distributed system is thousands or millions of elements, and they're all loosely coupled. They're communicating through message passing and so on, and they're solving a common goal. So that big machine room, maybe half of that was working on some big genome problem. And so the tools here, of course, are message passing, which we talked about, distributed shared memory, which we sort of hinted at a little bit, RPC we talked about. So a lot of these things we've done in the class are there, but distributed computing's no piece of cake, right? So there's things that fail, or maybe they fail partially. There's asynchrony, right? Because things are happening kind of at their own time and place because everything's so distributed. The scale is sort of ridiculous, right? Lots of thousands and millions of elements. And of course, consistency is a big problem because if you store a lot of copies in that system, how do you know that they are all up to date with each other? And we touched on consistency last time a bit, and how to use basically quorums as a way of getting consistency. But the consistency issue is nowhere near as solid as when we talked about ACID semantics, where C was the consistency there, because these systems are just too big. Okay? We talked about how network partitioning can be an issue in consistency last time when we talked about distributed file systems. Well, we can worry about the network being partitioned just in one of those big rooms, Right? What happens if one side of the room can't talk to the other side? Now I've got a network partition inside my machine room, okay, which is this huge thing. And so what's the difference between distributed computing and parallel computing? Basically, distributed computing is parallel computing plus failures that you have to deal with well. And that's really where this has gotten interesting, because how do you take so many components and make them do something when they're failing all the time? And so, this was actually, in the early 2000s, this was a buzzline. Data center is a computer. Okay? But now it's really true. Okay? I mean, here's this huge machine room, and this is treated as one computer that's built from less reliable components. The performance varies all over the place and so on, and it's really hard to program in many cases, but that is a cloud center. And if the data center or cloud is the new computer, what's the operating system? Now, we're not talking about the host operating system, so every one of those computers probably has Linux running on it, but that's not the interesting question. The question is, what's the operating system for the whole system, right? And could be equivalent in benefit maybe as what used to be called the LAMP stack back in the .com days. What does LAMP stand for? Well, it's Linux, Apache, MySQL, and PHP, although it's sort of branched out a little bit. So the Linux OS, Apache Web Server, MySQL, or MongoDB, or MariaDB, and then maybe PHP or Perl or Python. Come up with your favorite P word. Okay, and you could probably even put an R word like Ruby or something in there, but then it would be Lammer. Not as interesting, I guess. Okay, so come on. So classical operating system, you share data how? Well, inter-process communication, RPC, files, pipes. You have programming abstractions which come from libraries and system calls. This is the topic of the term, right? And you multiplex resources through scheduling and virtual memory and file allocation and protection. These are all the topics of our term here. What happens in a data center? Here, data sharing comes up from things like the Google File System or key value stores. Or Hadoop Distributed File System is an Apache version of this. What are programming abstractions? Well, maybe MapReduce or Hadoop or Pig or Hive or Spark. These are all names of abstractions that people use. And how do you multiplex resources? Well, you use something like Mesos or Yarn or Zookeeper or Bookkeeper. There's a lot of these. Okay, so our schedulers that we talked about become these, which schedule in that huge machine room. Our abstractions become these, MapReduce. Our data system becomes this. So it's a whole different animal. And Google was kind of the beginnings of a lot of this stuff. So they published a paper on the Google File System in 2003, which was this distributed system for the entire cluster. Kept 3 copies of everything. It's an interesting read if you guys do a Google on it. No pun intended, right? They also came up with MapReduce in a 2004 paper. How many people have heard of MapReduce? Good. Most of you, right? Because that's what do they do? That's 61C, right? And then Apache came up with open source versions of this, like Hadoop Distributed File System and Hadoop MapReduce. And so, what are some insights from all of this activity in the cloud? First of all, we're talking now petabyte is a standard term. I have a petabyte of storage, right? How big is that? 10 to the, what's a petabyte? 15, yeah. Okay, and this is becoming sort of old hat. But blocks, we were talking about 4K blocks, right? Blocks in Google File System or these things are 128 megabyte size blocks. Okay? All right? Data is striped on hundreds or thousands of servers. Why? Well, if you scan a 100 terabyte image on one node, what does scan mean? Scan means go through the whole thing. And suppose you can do 50 megabytes per second because maybe that's what your disk head bandwidth is. It's going to take you 24 days. And this, by the way, is exactly why you want to have RAID 6 as well, right? Because if a disk fails, it takes all that time to sort of repair. Scan on a 1,000-node cluster, 35 minutes, right? So if you've got a lot of 100 terabyte images, you want to do this on 1,000 nodes, not on one. Okay? So what else? Failures are going to be the norm. I hope you guys realize if you have a frequency of failure for one item, when you have 1,000 of them, your frequency of failure goes up by 1,000. So if your mean time between failure, say for one machine, is a node in 3 years, that's pretty good. But you put 1,000 together and you got one failing every day. Okay, so this is kind of unfortunate. And gee, since things are failing anyway, we might as well use commodity hardware. So Google is notorious for building their servers on the cheap. In fact, they brag about this. It's like, well, we're not going to buy servers from Dell or anybody else who makes them. What we're going to do is we're going to put together things from the cheapest components we can because we can already deal with failure. Okay? And then, of course, you can't have complicated consistency models, and so they do things really simple. Okay. So what's the programming model? You guys all remember this, right? MapReduce is you have a map function that takes a bunch of key values in and produces a list of output intermediate key and values. And then the reduce function basically takes a list of the same key and all of its values and turns it into an output list. And this is the biggest programming model of the cloud. And so basically there's the map and the shuffle piece. This is all stuff you've seen before. But the interesting thing about this is really tolerant to failures, because if any of these components, so we have all of my input data, I divide it up on a bunch of mappers. If any one of these fails, I just start another one. And if any one of the reducers fail, they set up so that you can grab the data back from the mappers and pick up. And so in theory, I can restart anything that's failed. I can put multiple of them if one of the machines is running slow. And so this particular model is not that it's so powerful, it's powerful enough, it's that it's really easy to make fault tolerant. Okay, which works great for these big machine clusters. And so, by restricting this key value model, I sort of do the same fine-grained operation you sort of learn about in 61C, but I do it on terabytes of data. The operations are deterministic, so I can do them over and over again. They're idempotent with no side effects, so I can restart at any time. And the only communication is restricted. Okay. And so what is MapReduce used for? At Google, it's used for indexing, article clustering, statistical machine translation. At Yahoo, it's used to build indexes, spam detection for Yahoo Mail. At Facebook, it does data mining, ad optimization, spam detection. All of that stuff is done with MapReduce. Okay? All right. I'm just about, let's see, are the HKN folks here? Yes. Okay, 1 second. So, pros of this is it's completely transparent, so it doesn't matter if I'm running on 100 or 1,000 nodes, the right thing happens. It's fault tolerant automatically because it's deterministic and I can restart. And it scales automatically as operations, there's no operations that are side effects, and so I can basically just add more nodes to it if I have a bigger job. Okay, and the load balancing happens just by adding more nodes in there. And so the cons, of course, is it's a restricted programming model. Okay, you can't always do everything as a MapReduce. And basically there's been a lot of follow-up research in the AMP lab. I'm not going to go into this now, but and other places. So Spark is an Apache project that started in the AMP lab that does a really nice job on iterative work. Pig and Hive are ways of doing high-level coding. And you can see a little bit why some of these are needed. Like here's a typical MapReduce job that sort of grabs given user data in one file and website data in another, find the top 5 most visited pages by users aged 18 to 25. I don't know what they're selling, but you could imagine. I guess that's your age group, right? And so here's MapReduce. Yipes. Okay, it's a little messy. And so Pig, I just wanted to show you this, lets you do the same thing like this. So there's a lot of effort in making things easier to code. Okay, and that's the translation. All right, that's all I really wanted to say. So what's the future here? It's going to be complete location transparency, mobile data encrypted all the time, computation anywhere, anytime, cryptographic-based identities, so you guys are going to be known by your keys, not by anything else. Large cloud centers, fog computing, local computing. Whether the Internet of Things is going to catch up in its current view is probably hard to say, but something like the Internet of Things is going to be there. I think the Internet of Things is very exciting and scary at the same time, and so we're going to talk a bit about that on Monday, I think. And better programming models still need to be developed because this MapReduce thing is fine, but not quite there yet. Okay. All right. So we're going to get truly distributed things. We're going to have applications that are graphs of services, not a single cell phone talking to the cloud. That's going to be out. And we'll talk about this. All right. So I wanted to thank you guys for the class. Let's thank the TAs who are here. Everybody want to give them a hand? Yay.